Good evening, everyone. Today in this lecture, we'll be discussing about the potentials. And in the last lecture also, we discussed about the potential, but today we'll be discussing the potential and some of the problems on potential. And then later in this lecture, we'll be discussing about the equipotential surfaces as well. So let's begin with the problem. The problem is where to find the potential at origin O due to the given charge distributions. So this is the given charge distribution in this diagram, right? We have two charge distributions in this diagram, and we have to find the potentials at origin O due to all these infinite charge distributions, right? So let's discuss case number one first of all, part one, right? So you can see that we have placed a charge q at a distance of a, and then charge charge q at a distance of 2a from the O, and then again we are placing a charge charge q at a distance of 4a from the origin, and so on. Then the fourth charge will be at a distance of 8a from the origin, and so on up to infinity. And we have to calculate the potential due to all these charges at the origin O, right? We know that potential is a scalar quantity, right? And the total potential at origin O will be the sum of the individual potentials due to all these charges at point O, right? So we'll be writing the total potentials due to all the individual charges. For the charge Q, for the first charge, the potential at O will be KQ upon A, right? And for the second charge, potential will be KQ upon 2A, right? And for the third charge, the potential will be KQ upon 4A, and so on up to infinity, right? So this goes to the infinite number of terms, right? And we can write this potential as taking KQ upon A as common. So we'll be left with this series 1 plus 1 by 2 plus 1 by 4, right? Plus 1 by 8 and so on, right? Up to infinity. So we can only find the potential due to this charge distribution at O if we solve this series, this infinite series. And we can see that if we take any two consecutive terms in this series, if we take any two consecutive terms in this series, like first term, second term, and the first term, or third term, or the second term, or fourth term, and third term, and if we try to find the ratio of these terms, so it will be 1 by 2 upon 1, that will be 1 by 2, right? Or we find the ratio 1 upon 4 upon 1 upon 2, that will be once again equal to 1 by 2. So you can see that between any two consecutive terms, the common ratio is a constant. It means that the common ratio will be 1 by 2. And for such series, whose common ratio between any two consecutive terms is a constant, right? We call that series as geometric progression, and the sum of the that series is found using the sum of uh, geometric progressions, right? Infinite geometric progression, right? So it's a GP series, right? We can say that this is an infinite GP series, and the sum of infinite GP series is nothing, it's first term upon 1 minus r, where r is the common ratio, right? Where r is the common ratio. So a is nothing, is the first term, right? And r is the common ratio. R is common ratio, right? We call this as common ratio. And we can see that here the common ratio between any two consecutive terms, it's r equal to 1 by 2, and the first term is 1. So the sum of this series, that is 1 plus 1 by 2 plus 1 upon 4 up to so on, up to infinity, that's going to be equal to first term, that's first term is 1, and the common ratio is 1 by 2. We'll write it as 1 minus 1 upon 2, right? So that's going to be equal to 2, right? That will be equal to 2. So the sum of this infinite series is equal to 2. It means our potential at this point, potential V at O, because of this series, for case first, that will be equal to 2 times KQ over A. So this will be the potential at origin O, right? Because of this infinite charge distribution. And similarly, if we try to find the potential at O because of this charge distribution at origin O, right? So the potential here will be, it will be equal to KQ upon A. Then we have a negative charge, that's minus kq upon 2a, right? And then we have positive charge again, so it will be plus kq upon 4a, so on up to infinity, right? Up to infinity. So we can rewrite this equation as, that will be p is equal to kq upon a will be taken as common. So we'll be left with 1 minus 1 by 2 plus 1 by 4 minus 1 by 8 up to so on up to infinite number of terms. And we can again see that this series also forms a GP. It's once again a geometric progression of infinite number of terms. So from here also the sum will be nothing. That will be the first term, that's 1, and the common ratio if we find, in this case the common ratio will be equal to 1 by 4 upon minus 1 upon 2, that will be equal to minus 1 upon 2. So minus 1 upon 2 will be the common ratio here. So the sum of this infinite series will be kq upon a. The first term is kq upon a. The first term is, in this case, that's 1 upon 1 minus 1 upon 2, right? Right. So the potential here will be, the total potential here will be now equal to, that's V is equal to, so 1 plus 1 by 2 will be 3 by 2, right? It will be 3 by 2. So it will be 2 kq upon 3a. So 2 kq upon 3a. So it means that for this case, the potential at the origin will be kq upon a, 2 kq upon a. And for this case, the potential at the origin will be 2 kq upon 3a. So what we did in this case, we used the concept of geometric progressions, infinite sum of infinite terms in a infinite geometric progression, right? Series of geometric progression series, right? GP series. So that's what we used here. That's given by a upon 1 minus r. A is the first term and r is the common ratio. So let's move on to the next concept here, where to find the potential, due to spherical shell, right? It's a spherical shell given in this picture, right? So in this spherical shell, we can see that in this shell, we can clearly see that we have a shell of radius r, right? We have a shell of radius r. This is a shell of radius r, and plus q charge distribution, right? The plus q charge given to this shell, spherical shell, right? And it is uniformly distributed over the surface of this shell. And let's suppose the sigma is the charge density of this shell, that will be given by the charge per unit surface area of this spherical shell, that's q upon 4 pi r square. So that will be the sigma, right? It's uniformly charge distributed, right? The charge is uniformly distributed, and we have to find the potential due to spherical shell, right? And we know that inside the spherical shell, the electric field inside the spherical shell is zero, right? There is no electric field inside the spherical shell, right? The electric field inside the spherical shell is equal to zero. And outside, at any point outside, at a distance of r, at some point P, the electric field is nothing, that's given as kq upon r square, right? This is the electric field due to shell that we calculated in the previous lectures also, right? And from this electric field, we can find the potential. At some point, in a region outside this shell, and as well as in a region inside this shell. So one of the important relations between electric field vector and the potential is that electric field vector is always given as the minus dv upon dr, right? That's equal to minus dv upon dr. So it's a negative times the first derivative of potential with respect to r, right? So this is the relation, very important relation between the electric field vector and the potential, right? Very important relation. So we'll be using this relation to calculate the potential at any region. So from here we can see that our dv will be nothing. It will be minus integral of E dot dr, right? Minus integral of E dot dr, correct? And we know that in case of sphere, the direction of electric field vector is along the direction of this r vector, right? Or we can say that E dot dr will be actually equal to nothing, that will be E dr, right? Because here the electric field vector is along the direction of this dr vector, so the angle between them is 0 degree. So E dot dr will be E dr, right? Because cos 0 is 1. So this is our dv here. So if we integrate both sides on this equation, right? If we integrate both sides on this equation, so we'll try to find the potential. We'll try to find the potential at a distance of r, or we can try to find the potential at point P because of this spherical shell, right? And one of the important points about this is that we know that at infinity, the electric field due to spherical shell is 0, or we also say that at infinite distances, by reference we take the electric field equal to 0 and also potential to be equal to 0 at infinite distance, right, from the any charge distribution, right? Let's suppose if we have to integrate, if we have to find the potential at point P, we will integrate it from infinity to some this point r, right, from infinity to r, and we know the potential at infinity is equal to 0, right? And some potential will be there at this point P. Let's suppose V is the potential at this point P. So we have to calculate this potential at this point P, right? So potential at this point P, so this is integral of dV. So it will be nothing, it will be V, right? V minus 0, that will be equal to minus integral of E dr with the limits infinity to r, right? With the limits infinity to r. And we know that electric field at this point is nothing, that's kq upon r square. You can substitute the value of electric field at this in this equation. So v will be nothing, it will be equal to minus integral of kq upon r square, right? Kq upon r square dr, right? With the limits infinity to r. With the limits infinity to r. So taking this kq outside this integral, we'll integrate this 1 upon r square with respect to this r with the limits infinity to r, right? So it will be equal to minus kq, and the integration of 1 upon r square is nothing, it's minus 1 upon r with the limits infinity to r, right? So it will be nothing, it will be kq upon r with the limits kq upon r, it will be kq, so it will be kq plus kq here, right? And with the limits 1 upon r, limit will be infinity to r, right? So upper limit minus lower limit, right? It will be equal to v is equal to kq 1 upon r minus 1 upon infinity, right? So 1 upon infinity is nothing, it's equal to 0. So the potential here will be kq upon r. So it means that at this point P, the potential due to this spherical shell will be nothing. It will be equal to kq upon r, right? So kq upon r is the potential due to this spherical shell at this point P, right? So V is nothing, that's equal to kq upon r, right? Kq upon r. So one more important point here is that now this is the electric field, or this is the potential due to this spherical shell at a point P, right, outside this spherical shell. But we have to calculate the potential due to this spherical shell inside, right? So this is the outside potential, right? I will call it as VO, that's the outside potential, that's equal to kq upon r, right? But I have to calculate this electric potential also inside the spherical shell, right? Electric potential inside the spherical shell. We can use once again the same equation, right? Uh, E is equal to minus dV upon dr, right? dV upon dr, and we know the electric field inside is nothing, that's equal to 0. If the electric field inside is equal to 0, it means dV upon dr will be equal to 0. If dV upon dr is equal to 0, it means that V has to be constant, right? V has to be constant. V has to be constant. It means that inside region of this, inside the region of the spherical shell, potential is nothing, it's a constant, right? It's a constant, correct? So it means that whatever the potential on the surface, whatever be the potential on the surface of this shell, same will be the potential inside this shell, right? And if we calculate the potential on the surface, that will be kq upon capital R. It means that inside the region of this spherical shell, the potential will be equal to kq upon capital R, right? So this V here inside this spherical shell will be kq upon capital R. It means that potential inside the spherical shell will be a constant and it will be equal to kq upon capital R. It means that the potential will be same as on the surface of the spherical shell, right? So we can conclude two equations here. The equation first is that potential outside, right? Potential outside is equal to kq upon R, right? And the potential inside will be nothing. It will be equal to kq upon capital R. That's a constant. It means that potential inside the potential inside the spherical shell is a constant, right? It has a constant value and that is equal to nothing but kq upon R, right? It means that if we plot this potential versus R, right? If we plot this potential versus R, it means if we plot this V versus R here, V versus R, so it will be like this, up to surface, up to capital R, up to distance R, the potential is a constant, and then this potential is inversely proportional to this small r, right? So it will be varying like this. So this is how the behavior of this V versus R will be when we plot it outside as well as inside. So inside it's a constant, right? It's a constant. It means that it has a value kq upon capital R, right? And outside this region, it will be inversely proportional to R, right? So outside this region, it will be inversely proportional to R. It means that outside it will be 1 by R, right? And inside it will be a constant, right? So let's discuss here question number 2 with respect to the potentials. The question number 2 here is that find potential due to a given arrangement of shells, right? We have two shells here. You can see in this picture, we have two shells here, the shell A and the shell B, right? So A is the center of the inside shell and B is the point on the surface of the inside shell, right? And then C is the outside shell here, right? We have charge Q1 on this shell. The charge is Q1, right? On this shell, the charge is Q1. On this shell here, the charge is nothing. It's equal to Q1, right? We have Q1 charge here, right? On this shell here, the charge here is nothing. That's Q1. And on this shell here, we have charge Q2, right? And we have to find the potentials at points A, B, and C. At potentials at points A, B, and C. We have to find potential here at this point and at this point and at point C also, right? Let's try to find the potential at point A, right? Point A. At point A, the potential will be there because of this charge Q1, right? Because of this charge Q1, there will be a potential at A. And because of this charge Q2 also, there will be a potential at A. And because of this charge Q1, because of this shell, right? Because of this shell, the potential inside this shell will be the same as the potential on the surface of this shell. It means that it will be equal to KQ1 upon A, right? KQ1 upon A. And there will be a potential also because of this Q2 charge, and this point A is inside this Q2 charge, right? It is inside this shell C. So the potential because of this shell C will be KQ2 upon the radius of this bigger shell. The radius of this bigger shell. The radius of this bigger shell is nothing. That's equal to B. It means the total potential at A will be equal to K into Q1 by A plus Q2 by B, right? Q1 by A plus Q2 by B. Now, similarly, we have to find the potential at B, right? At point B. Now, the potential at point B will be once again the potential because of the charge Q1 on its surface. That will be KQ1 upon A, right? KQ1 upon A. And then there will be a potential because of this shell C, and the point B lies inside this shell C. So the potential because of shell C will be once again KQ2 upon radius B, right? So this is the potential at point B. Now let's try to find the potential at point C, right? potential at point C will be the potential. We can see that this point C is on the surface of this outside shell, and this point C is also the outside point, right? This point C is outside the outside point for this charge Q1 or for this inside shell, right? So it means that for point C is outside this shell, right? Outside this shell B, and point C is on the surface of this shell C, right? So it means that for outside, for shell B, it will be outside point. It means the potential will be KQ1 upon the distance, that is from A to C, that's equal to B, right? We'll write it here as B. And because of this charge Q2, it will be KQ2 upon B once again, right? We can take K upon B as common. We'll be left with Q1 plus Q2. So this will be the potential at point C, right? So that's how we calculate the potential at different points because of the spherical shell. So let's move on to this question number 3. In this question, we have to find the potential at points A, B, C, and G due to given arrangement, right? You can see the given arrangement is here. Once again, we have two shells here, right? We have two shells here. Uh, each of the shell has been given as both shells. Outside shell, we can see that outside shell has the charge. Outside shell has the charge 2q, right? The outside shell has the charge 2q. And the inside shell is having the charge plus q, right? So if we find the potential due to this charge distribution at A, B, C, and D, right? So we'll just try to find the potential at C and D. Rest you can do A and B, right? I will just try to find the potential at C and D. A and B you can do on your own, right? So C is the point which is outside this shell B and inside this shell D, right? So it means that the potential here will be equal to, it will be KQ upon R, right? Plus, and for this 2Q charge, it will be an inside point, so it will be 2KQ upon the radius of this bigger shell, that's 3. So this will be the potential at point C, right? And similarly, the potential at point D will be, because of this 2Q charge, it will be 2KQ upon 3A, right? And plus, because of this Q charge, it will be KQ upon 3A, right? So it will be nothing, it will be 3KQ upon 3A. So this 3 and 3 will get cancelled. We'll be left with KQ upon A, right? So this will be the potential at point D, right? Because of the charge distribution given, right? So that's it with respect to the potentials. Now we'll try to learn about the equipotential surfaces. What are actually the equipotential surfaces, right? So equipotential surfaces are nothing. It's a region in a space, or we can say it's a locus of all such points in a space, right? It's a locus of all such points in space which are at same potential, or we can say that it's a space or a region, right, where each and every point are at same potential, or the potential difference between the 2 points is equal to 0. If the 2 points, if all such points in the space are at same potential, it means that the potential difference between the 2 points will be equal to 0 in a space or a region, and that region or space is what we call as equipotential surfaces, right? So those surfaces we call as equipotential surfaces, correct? So these are the surfaces in a space, or we can say these are the points or the locus of points in a space or in a on a surface where the potential between potential at each and every point is same, or potential difference between any 2 points is 0, right? Since the potential difference between any 2 points here is 0, it means that it has got some certain properties, right? There will be definitely some certain properties, certain important properties associated with these equipotential surfaces, right? So the point here is we'll discuss about the properties of this equipotential surface. One of the important property of equipotential surface is we know that there's a relationship between electric field vector and the potential difference, that's E is equal to minus del V upon del R, right? It means that in a space or a region, if there is a change in potential, then definitely there exists electric field, right? In a space or in a region, if there is a change in potential, then electric field exists. If V is constant, right? If V is constant, It means that in that space or region, the derivative of constant will be 0 or the electric field will be equal to 0. It means that for equipotential surfaces, since potential is constant in all those spaces, right? Or on all those surfaces, right? Each and every point on the equipotential surface is at constant potential, right? We can say that that region is at a constant potential, or the potential difference is 0. It means that there will be no component of electric field, along the direction of the surfaces, right? Or we can say no electric field no electric field exists along equipotential surface. I can write it in short ESP, that's EPS, that means equipotential surfaces, right? We can write it as EPS, correct? So along equipotential surface, there will be no electric field lines, because the reason is that because equipotential surface has a constant potential. If there's a constant potential, then electric field has to be 0 along that constant potential, right? In that space or in that region, right? That's the reason. Let's suppose we have this equipotential surface here, right? This is the equipotential surface. So along this surface, the electric field lines will be equal to 0, right? So E will be equal to 0 along this surface. No electric field will exist along this surface. Now, if electric field exists, then that electric field has to be normal or perpendicular to this equipotential surface, right? That electric field has to be normal or perpendicular to this equipotential surface. So that's the first property. We say that electric field intensity is always perpendicular to equipotential surface. That's a very important point with respect to the equipotential surfaces, right? So the point number 2 is that work done in moving a charge from one point to another point on equipotential surface is always equal to 0. It means that on equipotential surface, the work done, if we suppose this is equipotential surface, right? This is EPS. It means that this is a equipotential surface, and it means that each and every point on this equipotential surface will be at same potential V, P, and B, right? Let's suppose we are displacing a charge Q from this point to this point, or this point to this point, right? It means that we have suppose we have to do some work to displace this charge on this equipotential surface from one point to another point. Then the work done will be nothing that will be equal to the charge multiplied by this potential difference, right? Charge multiplied by this potential difference. That will give us the work done in displacing this charge from one point to another point. But we know that each and every point on the equipotential surface is at same potential. If each and every point on this equipotential surface is on the same potential, it means that the potential difference here between any 2 points on the equipotential surface will be equal to 0. If the potential difference is equal to 0, it means that work done is also equal to 0, right? So there will be no work done at all in displacing a charge on the equipotential surface from one point to another point. So this is property number 2 with respect to the equipotential surface. This is very important property, right? This is a very important property, correct? One more important property is that two equipotential surfaces can never intersect, right? Let's suppose we have two equipotential surfaces. If we have two equipotential surfaces, right? This is one equipotential surface, this is another equipotential surface, right? It means that if these are two different equipotential surfaces, right? If they intersect here, correct? So it means that we have two different potentials. This equipotential surface will be having a different potential, and this equipotential surface will be having a different potential. Now, if they intersect, so uh, it means that at the point of intersection, the potential will be same, right? For two different equipotential surfaces. But we know that for two different equipotential surfaces, the potential cannot be same. It will be different. So that's the reason we say that two equipotential surfaces can never intersect each other. So this is not possible that any two equipotential surfaces can intersect each other, right? So in conclusion, we have three properties, main important properties of the equipotential surface. Property number 1, electric field intensity is always perpendicular to the equipotential surface. Property number 2, the work done in displacing a charge from one point to another point on an equipotential surface is always equal to 0. And the third property is that no two equipotential surfaces intersect each other, right? So that was it with respect to the equipotential surface, general properties about the equipotential surface, right? So let's try to see equipotential surfaces due to different charge distribution, right? So we can see that here, this is the plus q charge, right? This is a plus q charge here, right? And it's an isolated plus q charge. It means that the electric field lines because of this plus charge q will be radially outwards, right? And spherically symmetrical, as we studied in the previous lectures also, right? So this is the electric field intensity E, right? This is the electric field intensity E here, right? This is the electric field intensity E along different directions, right? E is along different directions, correct? So we have to find the equipotential surface. It means that equipotential surface has to be perpendicular to that surface, right? Electric field has to be perpendicular to the equipotential surface, right? We can see that if we draw a sphere here, these are the spheres, right? These are the spheres 1, 2, and 3. If we draw these spheres, we can see electric field vector is always perpendicular to these spheres, right? To these spheres. We can see that each and every point on this sphere, right? Each and every point on this sphere will be at same potential, right? And we know that potential due to point charge is nothing, that's kq upon r, right? That's kq upon r. So each and every point is at the same distance with and the charge is also same. It means that all these points will be having the same potential, or we can say that this surface is nothing. This surface is a equipotential surface. So it means that for a point charge, which has spherically distributed electric field, right? For a point charge, the electric field vectors are spherically symmetric, right? Spherically symmetric. The equipotential surface will be spheres, right? So the equipotential surface for point charge will be a sphere, right? For point charge will be a sphere, right? Will be a sphere. So the conclusion of this point here is that for point charge, the equipotential surfaces are spheres in nature, right? So let's see the equipotential surfaces due to infinite line charge. We have this line charge, right? We have this line charge. We can see, we know that electric field due to any line charge, if we have this line charge here at a distance of r, and if we have to find the electric field, it's nothing, it's equal to lambda upon 2 pi epsilon naught r, right? For an infinite line. So this is the electric field vector. This is the electric field, right? And this electric field is directed like this, right? Radially outwards in circles, right? And this electric field is symmetric along a circle, right? So all the points here, right? All the points here, we can see that if we draw a slender here, every point on the slender, the electric field vectors will be normal to the slender, right? It means that equipotential surface for a line charge distribution will be cylindrical in nature, right? Will be cylindrical in nature. So it means that EPS, that's equipotential surfaces for line charge, will be a cylinder, right? So for line charge, the equipotential surfaces has to be cylindrical in nature, right? Here we have infinite sheet, right? It's a infinite large plane sheet, right? And we know that electric field due to large infinite sheet is nothing. It's equal to sigma upon 2 epsilon naught, where sigma is the charge density of that sheet, right? And this is a constant field, right? This is a constant electric field, right? Constant electric field lines are represented by the parallel lines, right? Parallel lines along the same direction, right? So you can see that if we draw planes here, these are the planes, right? These are the planes here, right? And we can see on these planes, the electric field lines are perpendicular. It means that along the direction of these planes, there is no electric field. If along the direction of these planes, there is no electric field, it means that on these planes, the potential will be a constant. On these planes, potential will be a constant. If on these planes, potential is constant, we call these planes as equipotential surfaces, right? These are nothing, these are equipotential surfaces. So it means that for a infinite charge sheet, the equipotential surface is nothing. It's a plane, right? Plane parallel to itself. So equipotential surfaces for infinite infinite charged sheet are planes, right? These are nothing. These are the planes, right? For infinite charge sheet, for infinite charge sheet, the equipotential surfaces are planes, right? So let's move on to the next topic, right? It's a very small concept that we already discussed earlier or also, right? So it's a relation between electrostatic field and potential. And we know that important relation between electrostatic field and the potential is E vector is nothing. It's minus del V upon del R, and the direction is along R cap, right? So if you have any potential which is radially varying, right? Radially varying, then the electric field due to that potential will be given as uh, it means that if we have any potential as V of R, right? Potential as V of R, then the electric field along the radial direction will be given by this partial derivative, right? That's E is equal to minus del V upon del R, and it will be directed along the radius, right? It will be directed along the radius. That's why uh, I use this radial unit vector, right? Radial unit vector here. Radial unit vector, right? And let's suppose if we have this potential V, it's potential V in Cartesian system. In Cartesian system, if the potential V is given as in Cartesian system, if the potential V is given as V of x comma y comma z, right? Y comma z, then electric field is nothing. It's given as minus grad of V, right? Minus grad of V, right? So minus grad of V, where grad is nothing. That's equal to it's equal to del upon del x I cap plus del upon del y j cap plus del upon del z k cap, right? So that's how we represent a grad. We call this as an operator, right? This is nothing, this is an operator. And particularly we call it as gradient operator, right? Gradient operator, correct? So this is a gradient operator in terms of in a Cartesian system, right? That's del upon del x I cap plus del upon del y j cap, right? Plus del upon del z k cap. And where these are nothing, these are the partial derivatives, right? These are not the total derivatives, these are the partial derivatives, right? These are the partial derivatives, correct? These are the partial derivatives, correct? So it means that we can find the electric field vector here as it will be nothing minus del V upon del x I cap, right? Minus del V upon del y j cap minus del V upon del z k cap. So this will be the x component of the electric field, this will be the y component of electric field, and this will be finally the z component of electric field, right? So if we take a gradient of a potential, then we'll get the electric field vector, right? So it means that gradient always gives us a vector, right? Gradient is always taken for the scalars, right? We take a gradient for the scalars and we get a vector quantity, right? Here, this scalar is potential. If we take the gradient of this potential, we get the electric field, right? Similarly, if we take a gradient of potential energy, then we'll get the force, right? Similarly, we can write force here as force will be nothing. It will be minus grad of U, right? Where U is nothing. It's potential energy, right? It's potential energy. It's nothing, it's potential energy. So let's try to apply this concept, right? Let's try to apply this concept in finding the electric field vector. And we know this electric field vector will be nothing. It will be minus del V upon del x I cap minus del V upon del y j cap minus del V upon del z k cap, right? This is the electric field vector, right? So let's apply this on one problem here, right? So the problem here is uh, we have been given a potential as a function of x, that's 8x square, right? 8x square is the potential, right? So this is the potential here, 8x square. And we have to find the electric field in the region. Since potential is only dependent on the x coordinate here, it means that the electric field will be only directed along x direction. It means rest of the component of this electric field will be equal to 0, or we can conclude here Ey is equal to Ez, that's equal to 0, right? So if we find the x component of this electric field, that will be equal to E vector, that will be minus del V upon del x, right? I cap, that will be equal to minus del upon del x of V, that's 8x square, I cap. So taking the derivative, so it will be minus 16x I cap. So this will be the electric field due to this potential. Similarly, if we are asked a question like this, if the question is of this nature, right? If the potential varies as x square plus y square plus z square, right? So this is the potential, right? Then how will we find the Ex, that's the x component of the electric field, then Ey and Ez, right? Ey and then Ez. So we can find Ex as, Ex will be nothing. It will be equal to minus del V upon del x I cap, right? So it will be equal to uh, minus del upon del x. V is nothing, it's x square plus y square plus z square, right? I cap. So since we are taking the derivative with respect to x here, so y and z here will be a constant, right? We'll treat y and z here as a constant, right? In this case, y and z will be a constant, right? So derivative of y and z with respect to x will be 0, right? So ex will be nothing, that will be minus del upon del x, x square, right? That's equal to minus 2x, right? Minus 2x I cap. Correct. So this is Ex, and similarly our Ey will be nothing, that will be equal to minus 2y j cap, right? And our Ez will be equal to minus 2z k cap. Or we can say that E vector as a whole will be nothing, it will be minus 2 times xi cap plus yj cap plus zk cap, right? So this is the electric field vector as a whole because of this potential varying as x square plus y square plus z square. So we have found this electric field vector using the concept of gradient, right? So I think that's it for today. In the next lecture, we'll be discussing about the capacitors, right? We'll be starting with the capacitors. So that's it. Till then, take care and goodbye.